Hello, in this video we're in the simple linear regression setting, but we're going to assume that x and y are both random. In all the videos up until this point, we've always assumed that x was fixed and that y was random actually through the error term in the model. So here's the model that we're going to look at. Y is equal to some line plus some error. Now in the past we've always assumed this was xi was fixed. But in this model, we're going to let the epsilon be IID normal 0, 1 sigma constant variance sigma squared, so the normal assumptions. We're going to let x be IID normal with some mean and some variance, and the epsilon and the x's are independent, and that's for all I and j. Now, generically, x and y are bivariate normal. And so if you think of it in vector, you can think of it in scalar, but I like the vector. So x and y has some mean for the x and some mean for the y, and this is the variance covariance matrix. Now this is generically how to write it. So the mean of y here, technically we could take the mean of y and we'd get beta 0 plus beta 1 and then the mean of x, and then that's 0. So that would fill in that spot. So we're just kind of generically writing it. And the correlation is the covariance divided by the standard product of the standard deviations. Okay. So let's, we're not going to derive the MLEs. I actually have a couple videos on deriving the MLEs for the normal distribution and multivariate normal distribution. And so I'll pass the derivations off to this. But the derivation for the variance of the y's is actually the standard variance formula, but instead of dividing by n minus something, we just divide by n. Now, as a reminder, this is what we call SYY. So it's 1 over n SYY. And it's also SS total when we were partitioning the sums of squares. These are the same. Now the variance for the x's is the same thing, except we use the x's divided by n. So it's 1 over n SXX. The covariance estimate for the covariance, the MLE for the covariance, is 1 over n times the sum of this cross product. Now one note here is that if we take the x's and multiply it to the y, and then the x's and multiply it to the y bar, we get this. So we've done nothing. But this sum right here goes to 0. So this term goes to 0. So really, we can just think of it as this term. And this in the past is what we have called SXY. And actually many books and many videos actually just call it this, but I'm going to call it this I'm going to say reduced form. So that's 1 over SXY. The mean of the x's is the sample mean of the x's. The mean of the y is the sample mean. And so that means the maximum likelihood estimator for the covariance, the correlation, and the correlation was the covariance over the standard deviations. That means the MLE for the correlation, which we call R, is equal to, and we plug in the MLEs for what we just derived, which is this. And then generically you can write it like this: sigma y hat, sigma xy hat, sigma x hat, sigma y hat. So note that R is actually called the sample correlation coefficient, right? And it is it's the maximum likelihood estimate for the population correlation. If we square the correlation coefficient, we get this, and so we just end up squaring this, right? And the square root goes away and we get this. So now let's find these moments from first principle, kind of what I was saying earlier. We just generically did it. But now let's find the expected value of yi. And so yi was, of course, beta 0 plus beta 1 xi plus epsilon I. So the expectation goes into the random variables. This is 0, and that's the mean, whatever it is. So this is the mean of yi, and generically we called it mu y. The variance, the constant term goes away, beta 0 goes away, so it comes into the beta 1, but it has to come out squared, and the variance of xi plus the variance of epsilon. There's no, the covariance between them are 0, so there's no covariance term in this sum. This is sigma squared. This we were calling sigma x squared. So this is it. And that's, so generically, that's the variance of y. Now, y or IID normal with this mean and this variance. You know, right here. We could plug this in for here if we wanted to. Now, one interesting note though, if we fix x. So if we look at the expected value of y given x, so that means it's fixed. And then when we take the sum in, this is the only random term, right? Because that's fixed. And that's 0, so that's the expected value. And actually that puts us in the simple linear regression case that we've been studying the whole time, where x is fixed. The variance, when x is fixed, is just the variance of epsilon, which is sigma squared, right? Because these are constant terms and don't factor into the variance. So that means y given x, you know, is normally distributed. So it's IID with this mean. That should be a plus. I don't know why I have that as a, right? Because that's the mean right here. And then a constant variance sigma squared. The covariance between y and x is this. So we plug in what we know about y, and this is x. Then this is constant, so it goes away. And the covariance between epsilon and x is 0 because they're independent and they're both normally distributed. So really we're only dealing with the covariance of these two terms. So the constant beta 1 comes out, and it's the covariance of xi, which is the variance. So it's the variance of x squared. Now generically we write that sigma xy, right? It's the covariance. That's the covariance. The variance of our error term, and remember that is y minus the line. So then we go in. So this is the variance of y. The constant term goes away. So the variance of this, but the constant has to come out squared. And then it's minus 2 times the covariance of this term and this term, but the beta will come out as it's constant. So that's the covariance of x and y. Now this is sigma squared. Oh, where are we going? Oh, the variance of epsilon is sigma squared. That's one of the assumptions. The variance of y we just called the sigma y squared. Beta 1 squared, that's the sigma x squared, and then that's the covariance. Okay, so now let's plug in what we know. We know the variance of y was this, right? And then everything else. Oh, the covariance is written like this. You know, you back solve for it because we knew if you know the correlation, you can back solve for the covariance, and that comes down. Now look. When we subtract sigma squared, those go away. We have 2 of these, so we can divide everything by 2, and we take that to the other side and divide and solve for rho, the correlation, and that's equal to beta 1 sigma x sigma y. Okay, so that is an yeah, that's the correlation, or that's the. Now go back to the MLE. So we needed this to derive the MLE. So from 8, which is this one, we know that beta 1, right, if you kind of back solve for beta 1, divide that over, we get this. And that is equal to, remember the correlation is this, and then this stays the same, and the y's cancel, the sigma x becomes sigma x squared, and that's the covariance. So now the invariance property of the maximum likelihood estimator, we just plug in the maximum likelihood estimators for these, which we said was SXY divided by N, and this is SSX divided by N, but the 1 over N's cancel, and this is it. So this is the MLE for beta 1. Now note that this is exactly the same as when X was fixed. It's the same estimate. Now from 1, we know that beta 0 is the mean minus beta 1 mean. Okay, so let's go back here. So here was 1. So the mean of y we said was, right, we're finding the mean, and it was this. So basically we're solving for beta 1. And that's what we get here. So now to find the MLE for beta 0, we plug in the MLEs for each of these. So that's y bar. That's the MLE for beta 1, so beta 1 hat, and the mean for x mu x is just x bar. So that's it. So that's the sample. That is the maximum likelihood estimator for beta 0. And it's exactly the same as when x was fixed, which I find quite fascinating. So now from 2, we can back solve for sigma. Really, we found the variance of y, and that was sigma squared plus this term. So we back solve for sigma. Now, so now we want to find the maximum likelihood estimator for sigma squared. So we've plugged in the maximum likelihood estimators for these. And the maximum likelihood estimator was the variance, was 1 over SYY. Maximum likelihood estimator for beta 1 is beta 1 hat squared, right? And this is 1 over N SXX. Okay. So now, remember that this was equivalent to what we called SS total, sum of squares total. And then in previous video 8, we showed that the sum of squares regression was actually equal to beta 1 hat squared SXX. So those two combine to this. Now the 1 over N's come out front, and the sum of squares total minus the sum of squares regression is actually the sum of squares residual. And that's it. So that's our maximum likelihood estimator. It's this. Now remember when back in PV4 I said this is kind of makes sense as a good estimator, but then we found the unbiased estimator and we divided by N minus 2. And so, but this is the maximum likelihood estimator for sigma squared. So for an unbiased estimate of sigma squared, we would of course divide by N minus 2, but here we're not. Now the coefficient of determination, which is the sum of squares regression over the sum of squares total. Now in PV8, which is the same result we did up here, right? We plugged in sum of squares regression, which is this. And of course this is just SYY, we know that. And then we plug in for beta 1, the maximum likelihood estimator for beta 1 is beta 1 hat, which is SXY over SXX. Of course we have to square it. That stays the same, stays the same. One of the x's cancel, right? And we're left with this. Right? So this is the maximum likelihood estimator for a coefficient of determination, which we'll call little r squared, right? And it is, right? If we take the square root of that, then we get r. So that says the coefficient of determination is actually the square of the sample correlation coefficient. Now, interpreting the correlation row. Now from 8, we get this relationship. And in 8, let me flash it. In 8, we got this. So if we square everything, we get this. And then from 2, we get this relationship. So that says rho squared, if we plug in what we have for beta 1 squared, which is this, and that stays the same. Now this cancels with that and we're left with this. So that's 1 minus this. And we know that the sigma y squared is actually bigger than sigma x squared, right, by design. So that tells me that rho squared is always less than 0. And it actually has to be greater than or equal to 0 too. So I probably should have put that. So let's do that. Right? Because if the sigma squared equals sigma y squared, then it's 0. But that implies that the correlation coefficient is between -1 and 1, when we kind of knew that. Now note that this relationship, right? We squared it here, but we have this. And that says that, and this is always positive, the standard deviation is always positive. So what if the correlation is negative, that means the slope, beta 1, is negative. It's positive, it's positive. So correlation, rho and beta 1 have the same sign. And that's going to be important when we do tests. So now that was all build up for the next video, which is we're going to look at a hypothesis testing about the correlation. And actually that's what we're interested in, right? We're using X to model Y, and we want to know, is there a significant correlation between X and Y? So is X really good at helping us predict Y? And that's what this test is going to be. And I hold it off because I want to derive it. And so we develop the test statistic, we derive its distributional properties under the null hypothesis, and etc. And you know that I like to get into that type of detail. And it would make this video too long. Well, that's all I have for this video. Hope you enjoyed it. I sure did. Please like it and subscribe so you don't miss the next one. Thanks. Bye.